Right, so in this talk, I want to tell you about how non-Hermitian topology can enrich the physics of electronic quasi-particle excitations in many-body systems. And two comments up front. So compared to the previous speaker, I will not be able to tell you about specific interesting properties of specific materials, but I will have to zoom out to some, let's say, more conceptual flight height to tell you about how these concepts of non-Hermitian topology enter quasi-particle physics in general. And then second, this being an expert audience on computational quantum many-body physics, I will focus all my introductory efforts here on the concepts of non-Hermitian topology, which I assume to be less familiar. So why are we considering non-Hermitian systems? Very generally, the motivation is that this makes sense when we consider a system that is part of a bigger system, can be coupled to a bath, for example, traditionally. And then these non-Hermitian Hamiltonians, which make energy complex in general and time evolution non-unitary, are somehow just an effective means to model dissipation and the complex eigenvalue specifically, then model decay, or if we have, let's say, an optically active system, maybe also amplification if there are positive real parts. And this has become an effective, at least approximate description in a wide range of physical settings, maybe originating from photonics and quantum optics as an approximation, effective non-Hermitian Hamiltonian approximation to quantum master equations, but has now spread from classical media materials to quantum many-body systems. And what I want to focus on in this talk, as I said, is the platform of quasi-particles in solids. So if we consider a spectral function here, then infinite lifetime would correspond to a delta peak. And if we have this smeared peak here, then of course this would be a decaying function in real space. So there's some line broadening, which corresponds to a finite lifetime. And we can model this in terms of a retarded Green's function, say, which now has a self-energy that has an imaginary part. Of course, you all know this. So what will be a bit more specific to this talk is that we now have a matrix structure. So it will be essential that we have a multi-band system, or at least a spin degree of freedom that non-trivially couples, because here not only an imaginary part in the self-energy, but also the matrix structure of the imaginary, or then more generally anti-Hermitian part of the self-energy will matter. And you can think of this as an extension to what's been known for decades, that if we have quasi-particles with a finite lifetime, we just add an imaginary part to some modes, or maybe dressed modes that we have to describe our quasi-particles. And here the point is that if the matrix structure of this self-energy part here, or the anti-Hermitian part specifically of the self-energy part, and our free Bloch Hamiltonian, if they are incompatible in the sense of not commuting as matrices, then we can have interesting physics which go beyond just adding an imaginary part to the modes that we would have otherwise in the absence of dissipation. And so the physical origin of this can be either coupling to a reservoir, if you have a lead attached to your system and there's a finite lifetime due to a surface self-energy that this lead introduces. It can be bulk interactions between particles, electron-electron interactions that cause dissipation and give rise to the self-energy. It can be disorder and a disorder average Green's function, and maybe additional things that I'm not covering here, but I will give you examples of these here. So then topology is the second ingredient at a very basic level. I'm interested here are these topological band structures where an insulating bulk or nodal points, like in the case of Weil semimetals here, are characterized by a topological invariant, and then as a consequence, there are anomalous metallic surface states via a bulk boundary correspondence, and there can be topologically quantized response functions such as a Hall conductance, and particularly interesting, the following will be these unidirectional or chiral edge states if we have a quantum Hall effect, or Chern insulator as a band structure, or here the surface states 2D chiral Weil fermions at the surface of a three-dimensional topological insulator, or then also these Weil nodes here, which lead to Fermi arcs. And for the starting point of non-Hermitian topology, I want to focus more here on these Weil points. So the Weil points can be seen as monopole charges of Barry curvature, and they're in some sense nothing different, or these Fermi arcs are nothing different from the familiar chiral edge states in the quantum Hall effect. So you can think of slicing this 3D system in 2D slices, and then at these nodal points here, the 2D topology, the Chern number of the system changes. So in my example here, the 2D slices are non-trivial in between the line connecting the two Weil points, and then you have the same, by bulk boundary correspondence, the same chiral edge states at momenta here projected to the surface in between the two Weil cones and the Weil points, and this is then gives rise to these bulk Fermi arcs. So this illustration here is from the paper here by Lorenzo Crippa, and much of the work on correlated electrons here. So you will see this name again. So the, let's say, junior scientist doing the heavy lifting in these projects is Lorenzo Crippa, and then senior collaborators are Giorgio Sangiovanni, and in this project also Massimo Campone. All right, so with this, let me go into the first part, exceptional topology of quasi-particles, and then to the extent that time allows, we will later look into spectral sensitivity of non-Hermitian systems as well. All right, so what's new about quasi-particles if we consider a matrix structure of this self-energy? So here we look at the anti-Hermitian part of the self-energy, sigma minus sigma dagger. And as I said before, we need this to be incompatible or not to commute with the band structure or the Bloch Hamiltonian of the system. And then this can give rise to effects if these two matrices are not simultaneously diagonalizable, that the anti-Hermitian part does not just add an imaginary part to the free system, or to the let's say dressed Bloch type Hamiltonian, but that it actually adds qualitatively new physics. And then, because if we are now interested in nodal points, so the generalization of these Weil points that I've been discussing before to non-Hermitian systems, then we also need to be in the vicinity to a nodal point, let's say Dirac or Weil type nodal point, because there's still ambiguity. So if this perturbation here, gamma, the anti-Hermitian one, is not huge, then it will only lead to a degeneracy, in a non-Hermitian sense, a degeneracy, if we do not start from a huge gap. So these are the two main ingredients, the non-commuting structure and the vicinity somehow to a band touching point. And you can see here one example that I will elaborate a bit more on later. So here you have this three-dimensional topological insulator, which has these chiral Weil fermions as surface states. So this is my ingredient number 2 here. And then we have this ferromagnetic lead on top, which is coupled in a dissipative fashion to the system. And the non-commuting structure here is very intuitive. So the ferromagnet has a fixed spin quantization axis that is preferred here, whereas the surface states have this texture, this spin momentum locking texture characteristic to topological insulator surface states. So they are incompatible and non-commuting. This can lead to the interesting effects. A second thing that you can see at this very general level, so intuitively, if you think about Hermitian systems, you would think if I add a magnetic perturbation to this time reversal symmetry protected topological insulator, then I would actually gap out the surface state. I would destroy them because I'm violating the protecting time reversal symmetry. But here instead, adding this dissipative magnetic coupling will stabilize this to a nodal phase in the non-Hermitian sense. And yeah, this is very characteristic because nodal points are actually more stable and more abundant, as I will convince you on the next slides, in non-Hermitian settings than in Hermitian ones. So to see this, let's look at a very, very basic example, a 2x2 matrix, not even momentum dependence necessary for now. And we look at the eigenvalues. So here you can already see one important feature. So instead of, if I had alpha and alpha star here in a Hermitian system, then I would have plus minus the modulus of alpha as a eigenvalue, whereas here I get the square root of alpha. And this is very characteristic. So from the degeneracy, which sits at alpha equals 0 here, I have these square root dispersions emanating rather than linear Dirac or Weil dispersions. Second important thing is, if we now look at the eigenvectors, they are first of all not orthogonal, and I have in general to distinguish right and left eigenvectors, but you can see that if I solve this explicitly, then at alpha equals 0, at the degeneracy point in energy, I get collinear eigenvectors. So not only the eigenvalues, but also the eigenvectors coalesce at this degeneracy, and this is known as an exceptional point. So that's something impossible in a Hermitian system where the eigenvectors always form a complete set. So here you can have this coalescence of eigenvectors, a matrix that becomes defective or non-diagonalizable, and at both these exceptional points. So now important question, if we add a momentum dependence, is how generic or how stable is this to occur? Is this just somehow fine-tuning or very exotic physics that will not occur in nature? And to look at this, we can just do a simple parameter counting. So we look at a two-band Hamiltonian. If we want a two-fold degeneracy, bands coming close to touching, we look at a two-band Hamiltonian, which is a linear combination of Pauli matrices and identity matrix. And the only difference now to a Hermitian system is that we allow these coefficient vectors in principle to be complex. So if we were constrained to the real part, then the equation here of the spectrum that you obtain simply by squaring the Hamiltonian would just end here, and you would see that all three components, because the length of this vector dr here would have to be 0, all three components of dr would have to be 0 individually. So this would be three parameters that you need to tune, drx, y, and z, to obtain a degeneracy. And that's the intuitive reason, of course, why we have stable Weil points in 3 spatial dimensions in solids if we think Hermitian. So now we have this imaginary part as well, and you now see under the square root that this equation here continues for the spectrum. And if we now want to identify a degeneracy, so that the splitting gap part here, the plus minus part under the square root is 0, then we have 2 real conditions, namely that the length at this momentum where the gap closes of the real and imaginary part must be the same, and that the angle, so the 2 vectors must be perpendicular, the angle must be 90 degrees. And that's only 2 real parameters that you tune now, which already gives you intuition that this is a more stable situation. Yeah? So I would only need 2 dimensions or 2 parameters, kx, ky in my band structure to make this generically occur. And this addresses a bit the question from my previous slide. Why, if I have this time reversal symmetry protected edge state of a 3D topological insulator, why I can now stabilize this by symmetry breaking perturbation if it has such an imaginary part. Yeah? Because I no longer need the symmetry. 2-dimensional surface state is now enough to make this generically stable. So you see here already abundance of exceptional points is bigger than abundance of degeneracies in the Hermitian realm. So this makes, if you like, exceptional points a bit of a misnomer, because if you have degeneracies, then they are very likely to be exceptional, right? But of course, it's justified in the sense that if you have a random matrix, the probability is still 0 to have any degeneracies, and you still need to tune 2 parameters, kx, ky. Right? You can also ask, how likely is it that if I have some dissipation, I'm at finite temperature also in my wire semi-metal, how likely is it that I will have a diagonalizable degeneracy, a traditional Weil point? And the answer is, of course, very unlikely, because if I now have real and imaginary part, and I want to make this degeneracy diagonalizable, then this means that not only the three components of dr, but also the three components of di individually need to vanish at this momentum. So this is 6 parameters. So if I add dissipation, it's even in 3 dimensions virtually impossible to find any diagonalizable degeneracies, which basically means if I zoom in to close enough resolution, any degeneracy that you find in reality will either have opened a small gap, or it will actually have become an exceptional point that you, where the splitting you can only resolve with better resolution. But to some extent, this simple parameter counting implies that in nature there cannot be something like a diagonalizable degeneracy. It's fundamentally unstable towards any generic part of dissipation or imaginary part. So now again, back to this symmetry protected topological insulator surface state that is now promoted to a stable point with a pair of stable phase with a pair of exceptional point. Can now make more sense out of this. So we have our 2 ingredients. We have our, without the magnetic perturbation, we have the Weil surface states, which are, however, fine-tuned or symmetry protected, if you like. And then we can override this to get a splitting into a pair of exceptional points with this characteristic square root dispersion here. And this will then no longer rely on symmetry. So if I now add an arbitrary perturbation, including a Hermitian magnetic perturbation here, then this will only change the distance between the exceptional points. But before this pair here of 2 exceptional points has actually met in momentum space and opened a gap, I cannot remove this anymore. Right, this becomes even more interesting, or somehow more stable, this game of non-diagonalizable degeneracies, if we add symmetry. So this has been so far without any symmetries, and there's a whole zoo of symmetry classes which has been started by Bernard and Leclerc here in 2001, and later been completed and elaborated on by many other authors. But here I want to focus on the effect on the co-dimension or the abundance of exceptional points of degeneracies in non-Hermitian systems. And if you have a symmetry that somehow relates the spectrum to its complex conjugate, such as this chiral symmetry here, note the Hermitian conjugate here in the equation. So Hamiltonian is up to minus its Hermitian conjugate up to a unitary transformation. Then it turns out in my simple two-band model before, this implies already one of the conditions. So the overlap of these 2 vectors, dr and di, is already pinned to 0 by this symmetry constraint. And this means that I only need one parameter to tune to an exceptional point. This means if I have a symmetry such as chiral symmetry in a list of related other symmetries, then I expect such degeneracies to occur in one spatial dimension, and this has been generalized later here to arbitrary dimensions and symmetries in the symmetry classes. And it turns out that for these symmetries that relate complex conjugate parts of the spectrum, we have that actually the codimension is cut in half. So n here is the degree of the degeneracy. I've discussed twofold degeneracy, n equals 2 so far. And without symmetries, this was 2 times 2 minus 2, so 2. And it was reduced to 2 minus 1, so to 1 dimension if I have this chiral symmetry. But in general, you see that it's not reduced by 1, but it's actually cut in half. And this makes, in principle, in physically relevant dimensions, up to 3 spatial dimensions, even higher degeneracies, stable threefold degeneracies in 3D and fourfold degeneracies in, threefold degeneracies in 2D and fourfold in 3D. So now let's look at this one-dimensional system. So we have a concrete microscopic model system here, where the ingredient, which in the end gives this interesting matrix structure to the self-energy, is just a sublattice dependent interaction. So you kind of think of one strongly correlated orbital, which is your A sublattice, and a weakly correlated, which is your B sublattice. And then, of course, scattering rates will also depend on sublattice in the end. And this will give, in this AB sublattice space, an I times sigma Z structure to the anti-emission part of your self-energy. And you see that here in this dynamical protocol, where you quench a system in an insulating initial state to close to a critical point in this 1D system, then actually the steady state that forms in this dynamics contains such an exceptional point. And you can see in very basic properties here, such as the spectral function, you can nicely recognize this exceptional point feature and this degenerate arc, which is the counterpart of the Fermi arc in a wild semimetal here in these observables. We can also, so this was a one-dimensional system where, thanks to chiral symmetry, you stabilize a twofold degeneracy here with Lorenzo and Giorgio Sangiovanni, Lorenzo Crippa and Giorgio Sangiovanni. We also explored the three-dimensional system where you have where you want a four-fold degeneracy, or you expect that four-fold degeneracies could become stable. And this is a four-band system illustrated here. So the color are the four different orbitals. And we have, in the simplest case, interactions only on one orbital, the yellow one. And then we have some nearest neighbor interactions in this lattice, which are illustrated by these bonds. So the model is a bit intricate. That's what I mean by it's not close to one of your favorite materials, maybe, but the structure is still only nearest neighbor couplings in this lattice system, and dominant interactions on one orbital. Again, no fine-tuning, so you do not need to have exclusively interaction on the yellow orbital. It can also be just stronger than the one on the other orbitals. And then generically, if you have chiral symmetry in this model system, you would stabilize these exceptional points, which are hallmarked by even steeper dispersion. So this would then go like the fourth root rather than the square root dispersion, such a fourth order exceptional point. So now we can push this one level further, because in the two preceding examples, I've always explicitly planted the matrix structure in the self-energy by saying scattering rates are bigger on the yellow orbital, on the other case, on the A sublattice. So now the question was, can this also spontaneously emerge in a system that doesn't have any preference, so that where I do not build in some matrix structure into these into the self-energy? And here the answer is yes. So a spontaneous symmetry breaking can in principle also do the job. So you can think of this at very high temperature being described by or at low interactions, whatever you want to tune. You can consider this as a magnetically disordered system, which is a three-dimensional topological insulator, or here weak three-dimensional topological insulator, which has these surface states similar to the ones discussed before. So 2D surface states protected by time reversal symmetry. And now if you increase interactions, or you start to lower temperature at a given interaction strength, then you pass through an extended phase here, where this model is where the system is not really a stable ferromagnet, like at very low temperatures, where you just have a bulk ferromagnet and the Hermitian part of strong magnetic moments that are ordered is dominant. But here, in some extended temperature region, you have driven by magnetic fluctuations at the onset of magnetic order. You have this imaginary part, similar to the dissipative magnetic lead, but somehow as an intrinsic property of the system that then leads to this exceptional point structure as a consequence of spontaneous symmetry breaking. So you can think here of a system that is at the onset of magnetic order, and this spontaneously gives different scattering rates to spin up and spin down in some emerging spin quantization axis. And again, this spin quantization axis is incompatible with this chiral texture here in spin of the topological insulator surface state. So this adds our two ingredients. We have a gapless surface state, which is symmetry protected or fine-tuned, and we stabilize it to a system that no longer relies on symmetry, but that somehow is, as a non-Hermitian topological system, stable in two spatial dimensions. Right. So now, as a final step in this hierarchy of how abundant or how stable are these phenomena if you add some dissipation to a many-body system, we can now relax the conditions even a bit more. And I now want to argue that even without symmetries, you will see nodal spectra in spectral functions as a topologically stable phenomenon in one-dimensional systems. So that is somehow from three-dimensional systems where you have stable Weil points in a Hermitian system, we can now go 2 dimensions down if we look at it from the angle of what we would see in a spectral function. So why is this? Well, I've motivated exceptional points as complex degeneracies or degeneracies in the complex spectrum of a non-Hermitian matrix. And then I would need 2 parameters to arrive at such a degeneracy. But the point is, of course, that if I have a complex spectrum, let's say in this plot here, you have a real and imaginary part of a 2-banded system as a function of momentum here in the vertical direction. And then what I would see in a spectral function is, of course, a projection of this onto the real frequency axis, right? And I would see the size of the imaginary part only by how sharp this mode here is. So the right moving mode here is very sharp in my spectral function, and the other one is almost entirely blurred. So this gives some insights into that there's a splitting in imaginary parts. So I'm actually not at an exceptional point. I do not have a complex degeneracy. But of course, I still see that this, if let's say my Fermi energy here is at 0 frequency, that this still crosses the gap. So I have I observe a gapless spectrum in this system. Sorry about that. And now the question is, how is this topologically stable? So from parameter counting, it's quite intuitive, because to see a crossing in a spectral function, actually only the real part of these complex spectra need to cross. And that's one less parameter than if I want a complex degeneracy, an exceptional point. But the topological stability you can also see from this picture here, that now because of Bloch's theorem, if I go once around the Brillouin zone here from -pi to pi in vertical direction in my illustration, then the set of the 2 eigenvalues must come back to the same pair, right? But they can have switched partners in principle, so they can in some sense have braided around each other. That's maybe a bit of overshot for 2 bands swapping, but I can have more bands and they can form in principle arbitrary braids. But the point is that then if you follow now individual levels like the blue one, then of course I'm not back to the same point here for the blue one after 2 pi, but I have to go by 1 reciprocal lattice vector here to the orange one, and then again by another 2 pi to come back here. So it's perfectly compatible with Bloch's theorem, which only tells us that the total spectrum is periodic in the first Brillouin zone, that if I follow adiabatically individual levels, or adiabatic is a dangerous word here for complex spectra, but continuously individual levels, that then I would not be 2 pi periodic or not be periodic in the first Brillouin zone, but I would have these 4 pi periodic structures. And you can see that I can only change this situation and open a gap in this projection to the real part that I see in the spectral function if I actually move these bands through each other, the complex bands. So if I close also the gap in the imaginary part, and this would of course then amount to an exceptional point where both real and imaginary part are degenerate. So here in this picture, exceptional points actually emerge as the transition points between different nodal phases here for the spectral function. And you can see that if there's a non-trivial, any non-trivial braiding, then in the actual spectral function, which only cares about the real part, I will always have this situation that I actually cross the gap. If you look at this plot here again, you also see another very interesting feature, that this is obviously non-reciprocal, the spectrum. So you have a situation where the right-moving mode is very sharp. So this almost looks like the chiral edge state in a 2D topological system that I've been discussing on one of the first slides. And of course, this is not violating Bloch's theorem or fermion doubling, anything alike, because I do have the left-moving one. It's just completely blurred here, and this can, of course, in principle, be to an extent that if I do an experiment, it could look like I really have only this single chiral edge modes. So this can mimic the chiral or unidirectional in 1D transport of such an edge channel without the 2D bulk. And this paper here, we actually showed that if you look at the charge dynamics in the system, you can see this clear asymmetry, that to the right, where this wants to move ballistically here, where we have a sharp mode, we actually see this nice dynamics, and then it quickly dies out in the direction where it's blurred. So you get very asymmetric dynamics, and that's interesting because this has not been put explicitly into the model. So the ingredient is again just there's an AB asymmetry in the scattering strength, and this without any explicit directionality in the model will then somehow lead to such a behavior. And as I motivated from this braiding picture here, this is stable against any, it doesn't rely on symmetry, it's stable against any small perturbation once this crossing with a finite gap in the imaginary part is there. Right, let me check how I'm doing with time.
You are actually entering question time.
Oh, I'm entering question time. Okay, then I think I want to skip the second part largely with the answers, and maybe only mention very briefly here on one slide. So non-emission systems are also very interesting in the sense that if you change the boundary conditions of the system, for example, from a bulk system or system with periodic boundary conditions to a system with open boundary conditions, then again something happens similarly exotic to these exceptional points, where two quasi-particle modes can merge into a collinear one. What happens here is that the spectrum, which is actually focused on the gray circle here, which has this ring shape, so it has a winding around some point here in momentum space, which here in complex energy, which here signifies the signals the topology of the system, and then it completely changes. So I just change one matrix element from periodic to open boundary conditions, and then this spectrum here collapses to this red arc. And there's another very interesting feature during this collapse as a function of one small matrix element in a very big system. You can imagine that this spectrum must change very drastically. So there's also the interesting effect that if I introduce a very small coupling to a system with open boundary conditions, a very small coupling between the ends, then this mode here at 0 will shift very, very quickly as a function of the small coupling, actually exponentially fast in the size of the system. So rather than that you have a mini gap that decays exponentially with system size, you would actually have something that is enhanced in system size. And what we did here in this recent paper, because such phenomena have mostly been studied so far at the level, phenomenological level of non-Hermitian type binding models. So where you just by hand add some non-Hermitian term, then you get all these interesting effects, the spectral binding, the gray term, this sudden collapse and the sensitivity with respect to boundary conditions. And here we went the somehow more microscopic detour of starting from a Hermitian many-body Hamiltonian and changing the boundary conditions of the system here at the level of the actual many-body model, and then calculating the Green's function, single particle Green's function and self-energy of this model. We could somehow see if in a fully microscopic many-body system, all these effects that the spectrum of the two-point function or quasi-particle properties show, these extreme effects and sensitivity to small couplings, change the boundary conditions also there. And we find, let's say, this is all data for the microscopic many-body model, so that the qualitative effects actually are not in any sense artifacts of such an effective non-Hermitian type binding model, but do actually occur in real physics. And with this, I think, if I'm already in discussion time, I want to conclude, and I'm happy to take your questions. Thank you.
Thank you.
Thank you, Jan Carl. Are there any questions? Adam, please.
Hi, thanks for the interesting talk. So I know you didn't really get to it, but I see a very tantalizing piece of this conclusion slide. So I'm wondering, you know, the act of measurement is inherently going to, you know, introduce a system and external field to the system. And so I'm wondering, given the large sensitivity that these non-Hermitian systems can sometimes have, can you talk maybe about measurement-induced transitions in systems? Like
a very interesting point. So you think that the aspect of dissipation, or that you have some non-Hermitian perturbation, would be brought in by measurements being performed on the systems. Do I understand correctly? Or?
Sure, that could be one aspect.
Right. Well, so to some extent, of course, the type of dissipation that you consider in a quantum optical system, the quantum noise there can to some extent always be interpreted as the environment measuring the system and then discarding the outcome. So in this context, I would rephrase your question to, if I somehow keep information about the system, or I can even maybe feed back my information about the measurement outcome into the system, if this can lead to transitions. And I think there is actually one paper from Jens Bardarson's group at KTH Stockholm which discusses precisely this point. So how somehow influence on non-Hermitian or non-Hermitian influence changes if I use part of the information that is if I just treat it as a quantum master equation, also considered to be discarded. So if I use some of the measurement data somehow.
Very interesting. Thank you.
Can I make a comment, Olivier? Sure. Can you hear me? Yeah. Just for while Jan was talking, I actually made a connection. I thought about the connection between the two talks, even though you said at the beginning that there is hardly any. But actually, this ferromagnetic phase that you were showing in our, if you can go back, to that slide. That is very close to a quarter field. Yeah, this one. This is essentially a quarter field two-orbital model, actually, because one orbital is completely filled. And this, by pushing it even further to quarter filling, would be unstable towards orbital ordering of the same kind that Eva was talking in the first talk. So actually, it would be interesting to bring that also into the game, because it's there. It has been actually studied by Carsten and Dieter in a very old paper on a two-orbital model. It's interplay between orbital ordering and ferromagnet. It was just a comment that came up by trying to connect the two talks.
Okay, yeah, thanks for the comment. I mean, I wouldn't have seen this connection, but this is precisely what I was hoping for if I present this to this audience. So I'm aware that some of this seems to be, well, to be pessimistic, far-fetched maybe for some of you, yeah, but my hope is that you recognize some of the ingredients that can lead to interesting non-emission physics, and then maybe yeah, that you can advance this to a real material, or closer to a real material setting. So this was my hope. And I mean, the main take-home message in terms of, let's say, qualitative insights is that I think the general phenomena that whenever you have something close to a band touching point, that it would very generically, at least at a good resolution, actually turn out to be one of these phenomena that I've shown you. So either this crossing here, which is actually this swapping of complex bands, or actually an exceptional point along these lines here. This is the generic situation, and everything else would be very, very fine-tuned. Yeah? So the question is just, what's your focus? So do you really focus on very low temperatures, and you have stable Fermi-liquid physics also in the system, and then you could ignore what I'm saying, because you say, okay, we want to be very close at very low temperature and very close to the fixed point, and we don't see much of these splittings, or whether you have a material maybe at room temperature also, where you could see band crossings maybe more generically like this shape, rather than actually the Dirac-like shape, yeah? Because then dissipation would be quite strong, and you would expect that if you see any crossings, they are typically more something like exceptional points, or these nodal spectral functions, and it's close to impossible to have them as diagonal degeneracies from textbook Weil and Dirac points. So this is what is let's say, not far-fetched. This is what very basic parameter counting here tells you.
Yeah, thank you.